Alright, so this is one of our first problems in finding internal forces. This particular problem wants to know what the forces are in point C. And point C is right underneath this load. Okay, so if I were to cut the structure there, what side of the the structure you want to look at? So if let me kind of cover up. I can choose this right side, or I can choose the left side. Which one is going to be the least amount of work?
Right side.
Yeah, the right, simply because I don't need to know the reactions at A if I want to use the right-hand side. So I'm going to do that. Be a little bit less work. So my first movement here is to draw the free body diagram of the right-hand side. Now, we have to think about this. This point C is going to be a little troublesome. I can't really cut it right underneath the force. First of all, force kind of mathematically exists at a point. How do you cut a point? You really can't. But I can cut it just to the left or just to the right. So let's do just to the left first. So I'll just say, hey, this is just to the left of point C. So if I'm cutting it just to the left, then that 500-pound force at C is on my free body diagram. And that's a pretty important distinction. So this is 2 kips per foot, and all these loads at 500 pounds are really half a kip. And the distance is 10 feet. So there's my section. So now I'm going to determine what my internal forces are. Okay? So first I'm going to assume that I have a force in tension. So there's my axial force. There's a piece of... There we go. Now shear force, positive shear force is going to be up or down on this face? It's going to be up. Now why is it going to be up? And I'll put a little positive there to remind you, because how would this body move under that force? It would rotate that way, which is clockwise. And then my bending moment, positive bending moment, is in this direction. Why? Because it would tend to bend this thing up into kind of like half a smile. Any questions about that? For me right now, this is the most critical part of the problem. Cutting your free body at the point, making sure all the right forces are there, and assuming positive sign convention for your internal forces. After that, just drop back to statics and do statics. So first thing I'll do is sum moments. There's my positive sign convention when I sum moments, and I'm going to sum moments at the cut, which is right here. And because of that, shear force and axial force create no moment. So I just have the internal moment, which in my sign convention is negative. It's not a negative bending moment, it's just a negative moment. I've drawn it as a positive bending moment. That word bending brings a sign convention with it. If you just say moment, you choose. Does this first 1/2 kip force create any moment about the cut? No. When we mean just to the left, we mean just to the left. So there's really no moment arm. So effectively it has no moment. But these other two do create moment. What kind of moment do they create about A? Positive or negative? Nope. Negative. It's 50-50, right? So it's going to be 1/2 kips times 10 feet minus half a kip times 20 feet. And then what do I do about this 2 kip foot moment at the end? I add it up. Is it positive or negative under my sign convention? Negative. So I'll have minus 2 kip feet at the end. I just need to add all that up, and I can solve for my moment. It looks like my moment's going to be negative That's 5, 10, looks like 17. 17 kip feet. So what does that mean? That means my bending moment is negative. And how would you expect this beam to bend?
Frown.
Into a frown. And what's a frown look like in this particular case? It would come out and probably bend something like that. Kind of half a frown. I guess that'd be a smirk. Right? You guys see that? Remember, it can't rotate here because it's a fixed connection. Okay, what about, let's do the shear force and the axial force. So I'm going to do shear force. I'm going to sum forces in the y direction. I like to assume up as my positive direction when I'm summing forces, so I will. So looking at my free body diagram, my shear force is up. I got 1, 2, 3 half kip forces acting down, so I've got minus half a kip, minus half a kip, minus half a kip. Anything else? Any other vertical forces? No. So what is my shear equal to? Looks like 1.5 kips. And just to be complete, I'll sum forces in the x direction. I'll assume to the right is positive. And what do I have in the x direction? I have negative a, but it doesn't really matter. It has to be equal to 0. No axial force. So there's my bending moment, my shear force, and my axial force just to the left of C. Is it going to be different just to the right of C? I don't know. Let's find out. So now I go to the right of C. So what changes? The length of my element is pretty much the same. At 10 feet over, I still have my half kip force. At the very end, I still have my half kip force. I still have my bending moment applied at the end, 2 kip feet. But now, since I'm just to the right of C, I don't include this 500-pound force at C. That's the only thing you see different. I'm still going to assume positive axial force, positive shear force, and positive bending moment. Those are unchanged in terms of their assumed values. I almost solved the problem again. You probably see a lot of things in common. So I'm going to sum forces at the cut again. Sum moments at the cut, and make sure it's in equilibrium using right-hand rule for my sign convention. So I start off. This is again still a negative moment in statics. I have 2 moments. The first one is half a kip at 10 feet. Oh, I left off my unit, sorry. And then half a kip force at 20 feet. And at the very end, I have that 2 kip foot applied. So when I solve for the moment, what do I get? Negative 17. So it seems that my bending moment is really unaffected as I go from the left side of an applied force to the right side. It doesn't make a big change initially on my bending moment. Okay? Now, as I move farther and farther away, and this value here for 10 gets smaller and smaller and smaller, it will start to make an effect. But right now, just as close to the left-hand side as I can get, and then jumping as close to the right-hand side as I can get, the moment doesn't seem to be affected. Let's see what happens to the shear force. So if I sum forces in the y direction and make sure it's in equilibrium, what do I get? Well, my shear force is up. I have a half kip force down and a half kip force down, it looks like my shear is equal to 1. So what's happened to my shear force as I go from just to the left of an applied force to just to the right of applied force? Well, it was 1.5 kips on the left, and now it's 1 kip on the right. I lost half a kip. Why did I lose half a kip? Because this force is half a kip. So it looks like, just kind of anecdotally now, that the change in shear is equal to the applied force. And the applied force is what? Okay, when we talk about forces and structures, these forces are considered to be negative. Just like in SAP, remember when you put a force in that was acting down, you had to tell it was a negative force? It's the same idea. So if the change in shear is P, and P is negative, you can see the shear dropped by that amount. It went down. So this is not committed to memory. It seems to be I'm observing it from our results. But actually later, not today, but Tuesday, I'll show you mathematically that that's true. Let's just finish it up. Some forces in the x direction. Make sure it's in equilibrium, and all I have is minus a. So again, there's no axial force. So I did want to show you one thing that's kind of interesting. So if I plot the moment, say as we're moving along the beam, say in x, and I'm going to pick this point here to be point C. My moment as I come on the left side has some value minus. I drew it backwards. Let me cheat and say it's the negative moment. Okay, so it's going to come in at some shape, and it doesn't really matter what the shape is, but it's going to come in and be this value 17, and when it leaves, it's still 17. There's no change in the moment. But if I were to plot over kind of the same space the shear force at point C, well, I don't know how its shape is, but it's going to come in at some value of 1.5, and it's going to leave at some value of 1. So there's going to be an abrupt change in shear. Now, if you have to connect this beam together with some two different materials, and you have to put a splice joint here, which of these two shears do you need to worry about? The higher one. So you can see that in a design sense, you're going to really be concerned about shear forces at connections or at points on the beam, but you're probably going to be really focused on the biggest one, not so much the change as a designer. You still want to know what it is everywhere, and that's going to be our focus, but you're going to really identify the maximum value. Same thing with moment. When you go to design, you really want to make sure your structure can handle the biggest moment that it sees, either positive or negative. The only time that's different is in reinforced concrete. You really want to know the distribution of moment in the beam, and when your moment falls below certain values, you're allowed to use less and less reinforcement. So you can start optimizing or minimizing your reinforcement with the shape. And you'll have that capability in a week or so to know the complete distribution of shear force in given moment.
So what would be the answer, the correct answer? I understand.
That's a good question. What would be the answer? It asks for the internal shear force and bending moment at C. What's the internal moment at C? Negative 17. What's the internal shear at C? The complete answer would be just to the left, it's 1.5. Just to the right, it's 1.
So you want to have both. If there's a load passing through, you want to have both.
Right. Usually on the exam, because I want to make it a little more straightforward, I probably won't ask you for a point right underneath a force. But if I did, the question would be, you really have to tell me two values. One to the left and one to the right. All right, so any other questions about this one?